Welcome to UVU CS3060 Lecture 5.1, where we discuss the first come, first served scheduler. Now, we're going to use a diagram to help us understand how schedulers work. This diagram is called a Gantt chart. This Gantt chart right here shows us the time that a particular event happens, and it shows us which event is happening. So these are events or processes. So in this particular Gantt chart, we have process 1 that executes, then we have process 2 that executes, and process 3 that executes. These are the CPU burst times for these particular processes. So we have a burst here of process 1 that is 24 units of time. We could call it milliseconds. It could be some other measurement, but the burst time here is 24 for process 1. And then we have a burst time of 3 for process 2 and a burst time of 3 for process 3. Now, in the first come first serve scheduler, we have process 1 and process 2 and process 3 arrive at the same time. Now, these three processes need to be run in a first come first serve scheduler. So the operating system kernel is going to actually start at the top of the list and execute this process in the CPU and allow that process to run for that length of time. Now, in this particular, the Gantt chart, we have from 0, and ignore the number 2 here, to 24. That's how long process 1 is able to execute. Once process 1 burst is complete, it's either been interrupted or it's moved to terminate or wait. Now the scheduler will put process 2 into place. Ignore this number. The 3 units of time that process 2 executes brings us to time 27. And so at time 27, process 2 terminates, exits, or is interrupted. The scheduler at that point can schedule the next process, which is process 3. And process 3 will run to 30 time units. So this Gantt chart shows us at what times specific events happened. Process 1 was interrupted or stopped, and process 2 was allowed to run. Process 2 exited or was stopped and allowed process 3 to run, and these are the times at which it happened. Now, how long did process 1 take to wait before it started? Well, process 1 started at 0. So that the difference between process 1's so if we have here process 1, its start time actually, yeah, it's start time minus its initialization time. So it initialized at 0. It started at 0, so process 1 has a wait time of 0. Process 2, on the other hand, had an initialized time of 0 and a start time of 24. So the difference there is 24. Process 3, it had an initialized time of 0, and its start time was at 27, meaning it had a wait time of 27. This is the amount of time it spent in the ready queue waiting for that to happen. So the average wait time for the entire system is 0 plus 24 plus 27, all divided by 3. This is the average wait time for this particular system. Now, the average wait time is just one measurement that we want to calculate, the amount of time that it was actually sitting in its particular queue. We also want to be able to calculate the response time. Remember, response time is the time between when it was initialized and when it actually got to start. You'll notice that it's the same as the wait time for our particular processes here. This is true for non-preemptive scheduling, and first come, first served is a non-preemptive, let's write a proper N, non-preemptive scheduler. Meaning that when it comes to scheduling decisions, it cannot be interrupted. There cannot be an interrupt to move it back to the ready queue, and it cannot be interrupted if an I/O interrupt is received. So because it's non-preemptive, wait is the same as response. Now there is one other measure that we're going to work with, and that is the time it takes to complete or its execution time. And that is actually a measure from start to actual completion. So if we take the values, for this we need to measure what is called throughput time. So throughput time is going to be the time from when it terminate time minus the init time. Notice the difference here. For wait time, we have start minus the init, so we still use the init value here, but this is terminate. So for process 1, its terminate time was 24. It initialized at 0, therefore process 1's throughput time is 24. Process 2, its terminate time was 27. Its initialized time was 0. Therefore, process 2 has a throughput time of 27. And finally, process 3 terminated at time unit 30. It initialized at 0. Therefore, its throughput time is 30. Now, if we average those together, 24 plus 27 plus 30 divided by 3 is 81 divided by 3, or 27. And this is the average throughput. So our wait time is 17, our throughput time is 27, and this is also our response time. But this is only true for non-preemptive schedulers. These are the measurements that we should get for first come, first served. Now, I don't know if you noticed, but back here, we had with this particular scheduling, we had this very long, relatively long process 1 burst time with some very short burst times. And our response time was actually fairly large, simply because this process 1 sat out in front. Well, this resembles a situation that you're probably familiar with. If you've ever been in a nice, speedy little car trying to get on the freeway, but there's only one ramp that you're allowed to use to get onto the freeway, and you're following a semi-truck which is taking a long time to get up to speed. Well, in this particular case, when you're waiting for that particular truck to get up to speed, you're not able to move quickly and get on the freeway quickly the way that your little speedy car is designed to do it. Well, in operating system schedulers, we call this situation the convoy effect. The convoy effect is where we have short processes that end up behind long processes. And this is a big problem with the first come, first served scheduler. The first come, first served scheduler suffers from the convoy effect, completely dependent on the way the processes are set up. So let's reorder these processes. Let's move process 1 with this big long burst time of 24 time units to the end of our first come, first served list. Well, this is what the Gantt chart looks like. We have an initialize of 0 for everything. The first job, or the second job, process 2, runs for 3 milliseconds. Let's just use milliseconds. The process 3 runs for another 3, terminating at 6. And then we have process 1, which runs for its 24 millisecond burst time to a completion time of 30. So let's average those particular processes. Now, process 2 has a wait time of 0. Process 3 has a wait time of 3, and process 1 has a wait time of 6. And if we average all of those together, 6 plus 0 plus 3, now we get 3 instead of 17. So remember, in the previous order of the jobs, our wait time was 17, and now a 3 is a better improvement. But we're dealing with an issue of the first come, first served scheduler. How does the scheduler know that it needs to move these particular jobs to the end of the queue? Is there a way that a scheduler can say, ooh, you're going to take a long time, we're going to let quicker, snappier jobs execute before you? Well, in the first come, first served scheduler, we're completely dependent upon the order that these jobs are found within the ready queue. And so the convoy effect is actually a fairly common situation in first come, first served scheduling when you have a variety of different jobs, such as one very long CPU bound job that's performing perhaps many calculations, and lots of little I/O bound processes. This ends UVU CS3060 Lecture 5.1, where we discuss the first come, first served scheduler.